All right, so in this video, we're continuing our derivation of the D5h character table. And what we figured out in part one of this derivation was that there are 20 symmetry operations, and that those 20 symmetry operations fall into 8 classes. So I'm going to write those 8 classes on top of our character table. The order in which we list these is arbitrary, but I'm just doing the way that is standardly listed. So we have our identity, our two C5s, two C5-2s, our 5 perpendicular C2s, sigma H, that's a horizontal mirror plane, two S5s, improper rotation axes, and then also the two S5 3 times, and the 5 sigma Bs. So those are the 8 classes. Leave some room on the right here for functions that we're going to test, see how they what symmetry they have. And then on the left side here, we have our 8 irreducible representations. We know there's going to be 8 because one of our character table rules says that the number of irreducible representations, or vectors as we can call them, is equal to the number of classes. And we have 8 classes, so therefore 8 irreducible representations. I'm calling them for now just gamma 1 through gamma 8. We don't know what they are yet, and so we cannot assign them Mulliken symbols, which are just labels that chemists use to give them useful names that say some important properties of their symmetries. But if we don't know what their symmetries are yet, we have to just call them something arbitrary. So we're calling them gamma 1 through gamma 8. Then at this point, the next thing to do is take advantage of the fact that the first irreducible representation is always the totally symmetric irreducible representation, which means +1 values across the board. So all 8 values of this vector are going to be 1. That's sort of a freebie. Then the next thing, way I like to start off, is thinking about another character table rule, which is that the sum of the squares of the dimensionalities are equal to the order of the point group, or the total number of symmetry operations in the point group. Total number of symmetry operations in the point group is 1 plus 2 plus 2 plus 5 plus 1 plus 2 plus 2 plus 5, which is equal to 20. What this rule says is that 1 squared plus a squared plus b squared plus c squared plus d squared plus e squared plus f squared plus g squared must equal 20. And this is these are dimensionalities. So it tells us how many functions transform together as each of these vectors. And so these have to be whole numbers, and they have to be 1, 2, 3, 4, or 5. 90+% of the time, they're just going to be 1s and 2s. Only in the very symmetric representations, like tetrahedral and octahedral, do you have values of 3, or icosahedral, you have values of 4 and 5. So we're basically looking for values of 1s and 2s. And if you stare at this long enough, you can figure out there's only one solution to this, where you can only have 1s and 2s. And that's where you have 4 2s and 4 1s. Because if you have 4 2s, that gives you each of those 2 squares is 4, and 4 of those is 16. And then you have 4 1 squares, that's another 4. 16 plus 4 is 20. So that means on this first column, we can put 4 1s and 4 2s. So in other words, we are looking for 3 more one-dimensional irreducible representations and 4 two-dimensional representations. So that gets us, one step closer. At this point, the next thing to do is to test various functions. So I would start off with linear functions, and the easiest one to do is start off with the z function. So here what we're doing is we're imagining a z vector. So I'll draw it in red here as just a vector with an arrow. And we're thinking about how the direction of the z vector changes when we apply one symmetry operation from each class. Remember that all the symmetry operations in each class are mathematically similar, so they will give us the same result here. So that's the nice thing about grouping them into classes is we only have to choose one symmetry operation from each class. But we'll march along here and do this for each class and think about how one symmetry operation in that class transforms the z vector. So first, we think about identity operation. In the identity class, doing identity on anything gives you back itself. So z goes to z. Then we can think about the matrix representation that explains this transformation of z going to z. It's a 1-by-1 matrix with the element 1, not very interesting, but the character table tells us that we take the trace or the character of that matrix, which is the sum across the main diagonal, just a 1-by-1 matrix. So the character of this, or chi, as we use Greek letter chi, of the identity operation for this transformation is just 1. And so that tells us that a value of 1 is going to be under dimensionality. We already knew that because we derived it from the previous rule. Then we move on to the next class, which is C5. So we asked the question, how does the z vector transform when we do a C5 along the z vector, wrapping around the z vector? C5, remember, is a 72-degree rotation, wrapping around the z vector. So if we have a vector pointing up, we rotate that 72 degrees along the z vector. That vector, the base of the vector is going to spin maybe, but it's still pointing up. And so fundamentally that hasn't changed anything, and z goes to z. And again, we have this 1-by-1 matrix that explains this transformation. So the chi, or the character, of the C5 operation is also equal to 1. So now we can go up here into our character and put a value of 1 under the 2C5 class. Same exact thing for C5-2. That's 144 degrees rotation. Again, z is going to go to z. We're just wrapping it around the z-axis, so we're not changing anything. And I'm not going to write this out again, but z goes to z. Again, we're going to get a value of 1 for the character. Next one are perpendicular C2s. So those are 180-degree rotation. And we can think about which C2 to choose. They're 72 degrees apart from one another. But what we can do to make things simple for ourselves is just define the x-axis as going along the C2. And so again, we're thinking about one of the C2s, one of the 5 C2s. Again, we're thinking about this z vector and how it transforms. And so if we just define one of those C2s as wrapping along or being coincident with the x-axis, then it's quite easy to visualize what happens when we do a C2. Now, for these character table derivations, basically, you're always going to want the z-axis to be coincident with the principal rotation axis, the highest order n, which in this case is C5, right? Highest n value. And so that's sort of required. Otherwise, you're going to get the wrong values for how things are defined when people derive these character tables. But the x and y, it turns out, can be defined however you want. Of course, x, y, and z have to be perpendicular to one another. But we can just do that right now. So anyway, for this C2, we can see that if we take, and we're doing a 180-degree rotation, and if we do that, that's going to, along the x, right, we're rotating this way now, that's going to take a z vector and flip it into the negative of itself. And so our answer here is actually that z is going to go to negative z. And that means that there's a 1-by-1 matrix with the element -1 that describes the transformation of z going to negative z. We take the trace of that matrix, and the character chi of the C2 operation, therefore, is -1. And so now we put a -1 there. That's actually a good sign because it shows us that z isn't transforming as gamma 1, which we had already derived, but it transforms as something different because we have a -1 here. So we're using this as a way to derive a new irreducible representation. What about the sigma h? That's the next one. Well, the sigma h is in the xy plane. Remember, it's horizontal to the principal rotation axis, which is the z-axis. So we have this mirror plane here, and so the z vector is looking at itself in the mirror plane. It's above the mirror plane, so it looks at itself below the mirror plane. So z goes to negative z, and just like before, we get a value of -1 for sigma h. All right, and so our next one is the S5 operation. So for the S5 operation, we have to remember what an S5 is. That's a C5 followed by a sigma h. And we can do this quite quickly because we know a C5 did nothing, it just took z to z. And we know a sigma h took z to negative z. So we went z to z and then to negative z. So overall, z went to negative z. And so we're going to get a -1 there, just like before. S5 3 times, remember, was a C5 3 times followed by a sigma h 3 times. See the previous video, part 1. But that's equal to C5 3 times followed by sigma h. C5 3 times, it's just a rotation. So just like these other rotations along the z-axis, they're not going to do anything. So z goes to z, but the sigma h, as we just said, goes to negative z. So overall, this goes to negative z, so we get a -1. And then the sigma v's. The sigma v's all contain the z-axis. So because they contain the z-axis, we can write any one of them. I'll write the one that is, I'll draw the one that's in the xz plane. But because the z-axis is in the xz plane, that means that for sigma v, z also goes to z, or z goes to z, so we have a value of 1. So there we have it. We derived the character for the z value. So the next thing we're going to do is do the same sort of logic, but now for x. And so we can do that pretty quickly. So we're going to write down x here. And we're going to go through and start with identity. And of course, with identity, we're going to get x going to x. Okay, and then we go to the C5, right? The C5 is a 72-degree rotation wrapping around the z-axis. Remember, the z-axis is the principal rotation axis. And so what's going to happen here in this case? Now we're thinking about an x vector. That x vector, we're thinking about it rotating 72 degrees around the z-axis. So it's going to spin. And it's going to spin not quite to y, because y would represent a 90-degree rotation. And so what this means is that x is going into some linear combination of x and y. In other words, we can't describe x without also having y, and this vice versa is also going to be true. We're going to have to think about the x and y vectors together. Another way of saying that is x and y transform together. And so I'm going to move this down here and put x comma y, and it's going to be under gamma 5, one of these ones with the dimensionality of 2. So actually for identity, we have to think of x and y going together. X goes to x, y goes to y. Now I think of a 2x2 matrix that describes this transformation. The identity matrix, that explains how x goes to x and y goes to y. I now take the trace, and it feels a little bit more meaningful than the previous example of z, because now I have the character, or chi, of the identity operation is a sum across the main diagonal, which is 1 plus 1, which is equal to 2. We have a value of 2 there. All right, but what about C5? C5, we have to use the rotation matrix, which we've talked about this many times before in other videos, but that is cosine theta, sine theta, negative sine theta, cosine theta. Depends upon which way you define things, whether or not you have negative. But we're going to be rotating by 2 pi over n. N is 5 here. So we have cosine 2 pi over 5. That's another way of saying 72 degrees. We just have it in radians. Sine 2 pi over 5. Negative sine 2 pi over 5. And cosine 2 pi over 5. And so now when we take the trace of this matrix, we get chi of C5 is equal to cosine 2 pi over 5 plus cosine 2 pi over 5. And a nice compact way of writing that, it's just 2 cosine 2 pi over 5. So it's a non-integer value, but that's what happens a lot of times when you have these C5 axes. So under here, our value is actually going to be, oops, drew that in the wrong spot, right? I got to be next to xy. Our value here is going to be 2 cosine 2 pi over 5. Nothing about the character table tells you that you can't have non-integer values. So that's what we got for the first one. Our C5-2 is going to be very similar, but now we're going to have cosine 4 pi over 5, right? Because we're doing 144 degrees rotation. We have to rotate twice as much. And cosine 4 pi over 5. And notice I'm not even bothering to write the signs because I know that when I do the trace of the matrix, I just care about this main diagonal. And so the chi of C5-2 is going to be cosine 4 pi over 5 plus cosine 4 pi over 5, which is equal to 2 cosine 4 pi over 5. And so that's going to be our character under the next class. What about the 5C2? Well, remember we said the C2, we defined one of our C2s as wrapping around this x-axis, being coincident with x-axis. So if we do that, and we're rotating 180 degrees along the x-axis, well, that's going to do nothing to x. If we do that for the y vector, okay, that's going to spin us to negative y, right? Because we have a vector here, and then we're rotating it this way, and so it's going to spin it to the opposite self. So x goes to x, y goes to negative y. The transformation that explains this, or the matrix that explains this transformation, is 1, 0, 0, negative 1. That takes x to x and y to negative y, and so you get a trace of that, which is equal to 1 plus negative 1, which is equal to 0. So for C2, our character is just 0. All right, what about sigma h? Sigma h is in the xy plane, remember. And so if we're in the xy plane, that's not going to do anything to x or y. So x goes to x, y goes to y. We're going to get the identity matrix. 1's across the main diagonal. And just like we got for the identity operation, we get 2. 1 plus 1, sum across the main diagonal equals 2. Okay, now what about S5? Well, S5, what is an S5? Again, we think about this. It's C5 followed by a sigma h. Sorry about that. Okay, and so we know a sigma h didn't do anything, okay, to x and y. And so for that reason, we know basically this is going to behave, S5 is going to